All right, the second type of differential equation we're going to learn how to solve is called a linear differential equation. All right, a linear differential equation is written, it's a first order ODE as well. And it's written in this form: dy dt, derivative of y with respect to t, plus some function of t times y. So you get a little bit of freedom here because p of t can be any function of t as long as it's continuous, times y equals some function of t, a different function of t, as long as it's continuous. So you get a little bit of freedom. So these will kind of all look different because p of t and g of t can be different functions. Okay. How the heck do you solve these? Because they're not separable, because p of t and g of t are not the same. If they were the same, this would be separable. You could subtract it from each side and factor out, and then divide by y. But these are not separable. Okay. All right. So this is the logic behind the solution. Okay. All right. The first thing I'm going to do, I'm going to introduce a mysterious function. I'm going to call it integrating function. I'm going to kind of explain a little bit more what it is. The integrating function I'm going to call mu of t. Okay. A lot of these are solved by just tricks. And the justification comes after the trick is introduced, so it's a justification as opposed to deriving it. But I'm going to introduce this function. I'm going to call it mu of t. All right, here's another mysterious step. I'm going to start with my original ODE. I'm going to multiply every term by this mysterious function mu of t. So mu of t times dy dt plus mu of t times p of t times y equals mu of t times g of t. Okay. Now, look at the left side. This almost looks like the product rule, doesn't it? Mu of t times dy dt plus y times, if somehow mu of t times p of t was equal to the derivative of mu, then the left side would be the product rule. So let's say that this mysterious new function I introduced, the derivative of mu of t, is equal to mu of t times p of t. So I'm going to replace mu of t with p of t with derivative of mu. And now I do have the product rule on the left side. First times the derivative of second plus second times the derivative of first. So the left side is the product of mu of t times y of t equals to mu of t times g of t. And here I can just integrate each side. On the left side, I have mu of t times y of t plus c equals the integral of mu of t times g of t. Again, I have to kind of hope that it can be analytically integrated. And if it's a problem in the book, it probably will be. Okay. And then I'm going to subtract c from each side and divide by mu. So in theory, if I do this, I do actually can find the solution y of t. All right. So the question now is, what is this mu of t? Well, let's go back to this condition we imposed of it, that the derivative of mu of t has to be equal to mu of t times p of t. I'm going to divide each side by mu of t to get p of t equals mu prime of t divided by mu of t. Notice something. This is the derivative of the natural log of mu of t. Okay? Right? Because the derivative of ln of a function is the derivative of a function times divided by a function. So you can see where this is headed. Now you just have to solve for mu of t. Remember, p of t is given. That's given in the equation. So you know what this is. Now you have to solve for mu of t. All right, so you can see where this is headed, solving for mu of t. Integrate each side. You get ln of mu of t equals the integral of p of t dt plus k. And raise each side to e. So mu of t equals e to the integral of p of t times dt plus k. Use the properties of exponents to write this. And actually, I'm going to let mu of t just be e raised to the integral of p of t dt. The reason is because the constants end up all combining into one giant constant, okay? So so we're just going to keep this constant when you integrate each side here, but not this constant, because you can try giving everybody a constant, but eventually they'll just all group into one giant constant that you can solve for by using the initial value. All right, so mu of t is e raised to the integral of p of t dt. Okay, this is how you solve linear differential equations. Let me go over the process. All right, so first you have to make sure it's in this form. dy dt plus some function of t times y equals some function of t. Then you have to find something called the integrating factor, and it's mu of t equals e raised to the integral of p of t dt. Multiply every term in the differential equation by mu of t, which is what we did. And rewrite the left side using, because it's the product rule, as a derivative of a product of two functions. Integrate each side. Solve for y of t if possible. So we have to hope for a lot of things. We have to hope that p of t has a closed form integral. We have to hope that when you multiply g of t by mu of t, that has an integral, and okay, and this will have an integral because it's a derivative. Okay, so okay. All right. So let's take a look at two examples. Example 4, solve the IVP cosine of x times y prime plus sine of x times y equals 2 cosine cubed x times sine of x minus 1. And this is your initial condition, and this is the region of validity. Step 1, I have y in terms of x, but y can be in terms of t as well. So make sure the equation is in this form. Is it? Oh boy, that's hard to tell. But it looks like if you divide each sine by cosine of x, it will be. So I'm going to start with the original. I'm going to divide each side by cosine of x. So y prime equals sine of x cosine of x. Y equals this. Okay, so sine of x divided by cosine of x is my p of t or p of x. And then this insanity is my g of t or g of x. Try to simplify. Sure, why not? Sine of x divided by cosine of x is tangent of x. And then this insanity stays. Oh, 1 over cosine is secant of x. All right, so, okay, it is in the right form to be called a linear ODE. Step 2, find the integrating factor. Mu of t equals e to the... so mu of t or mu of x, e to the integral tangent of x dx. The integral of tangent of x is the natural log of the absolute value of secant of x. You can rewrite tangent of x as sine over cosine and do u substitution if you forget, but that is one of the standard formulas. So e to the ln cancel. Oh, because the region of validity is positive numbers, I can drop the absolute values, e to the ln cancel, you just get secant of x. So the integrating factor is secant of x. So step 3, write the original equation and multiply everybody by secant of x. So you get secant of x times y, secant of x times tangent of x, 2 secant of x times cosine squared of x, sine of x minus secant of x squared of x. The left side is the product rule for secant of x times y. So rewrite that as secant of x times y prime. On the right side, use secant of x times cosine squared of x is cosine of x. And then 2 cosine of x, you get 2 cosine of x sine of x. All right. Step 4, attempt to integrate each side. The left side is just secant of x, y of x. The right side, 2 cosine of x sine of x is 2 sine 2x minus secant squared of x dx. Yeah, whoever cooked this up, this does have an integral. So the integral of sine of 2x, you can use u substitution as negative 1/2 cosine of 2x, and then secant squared of x, that's in one of our standards, is tangent of x, because the derivative of tangent is secant squared. Okay, here we go. And then step 5, you can divide each side by secant, or multiply each side by cosine, which is what they do. And then the plus c comes here. So multiply each side by cosine. You get y of x equals negative 1/2 cosine of x times cosine of 2x minus sine of x times c cosine of x. You can't replace this with another constant like c sub 1 because cosine of x is not a constant. Okay, so the constant is added here. Okay. By the way, notice that if the integrating factor did have a constant, it would just divide out because you're multiplying each side by the integrating factor. So the constant would just divide out. All right, so that's my that's my general solution. And then to find so that's my general solution. To find a particular solution, I'm going to apply the initial condition. Y of pi over 4 equals 3 square root of 2. So plug in pi over 4, do the, evaluate the functions. 3 square root of 2 equals negative square root of 2 over 2 plus c square root of 2 over 2. So c equals 7. So that's my particular solution. All right. And then this is the graph. Notice that you don't just get plus 7, right? This is the first problem we have, that the particular solution actually... Well, no, that's not the first problem, but the constant multiplies a term in the particular solution. Okay, so that's problem 4. All right, let's try one more of these. Problem 5. Solve the following initial value problem. Ty prime plus 2y equals t squared minus t plus 1, and y of 1 equals 1/2. Okay. If you want to try to solve this on your own, pause and solve it on your own. Otherwise, we're going to go through the steps. The first step is to make sure it's in this exact form. All right, so start with the initial ODE, divide everybody by t, you get y prime, p of t is 2 divided by t, and then g of t is t minus 1 plus 1 divided by t, all these power functions, so this looks a little promising. All right, so step 2, integrating factor e raised to the integral of p of t. E raised to the integral of 2 over t dt, e raised to 2 times ln of the square, the absolute value of t. Apply the properties of x of natural logs to write this as e raised to the ln of absolute value of t squared. You get the absolute value of t squared, or just t squared. So the integrating factor of t squared. Okay, this looks promising. Maybe I should have done this as problem 4, but this looks promising because it's just polynomials as far as the eye can see. So step 3, you get just multiply everybody here by t squared. Rewrite the left side as a product of t squared times y prime, and then the right side becomes t cubed minus t squared plus t. Step 4, integrate. You get t squared y, 1/4 t to the 4th minus 1/3 t cubed plus 1/2 t squared plus c. Divide everybody by t squared. So that's your general solution. And then if you apply the initial condition, you get that c equals 1/12. So that's your particular solution. All right. All right, so you know how to solve 2 ODEs now. 2 first order ODEs. All right. And that's the graph of the particular solution. Okay. All right. Now you're ready to try a few problems on your own. And the problem set is due on the next B-Day, in quotes, April 7th, 2020 by 9 a.m. All right. Have a wonderful weekend.